In this video, we'll talk about the derivative as a function. We saw that the slope of a tangent line to a curve, y equals f at x, at a point on the curve is given by the derivative, which we call f prime of a. The value of f prime of a depends on which a you're looking at. As an example, consider the function f at x equals x cubed minus 8x squared plus 19x minus 9. This example was just chosen because it has a nice picture. The slope of the tangent line at the point 2, 5 is -1, and the slope of the tangent line at 4, 3 is 3. So we have the same curve in both of these graphs, but we're just looking at different points. At the point with coordinates 2, 5, the slope is -1. On the same curve, if we look at the point with coordinates 4, 3, the slope is 3. So the derivative at 4 is 3. Since the value of the derivative depends on the input that you give it, we can define a function, which is called the derivative function, and we define it using the difference quotient. If f is a function, we define the derivative function to be equal to f prime at x, which is the limit as h goes to 0 of f evaluated at x plus h minus f at x, this quantity divided by h. Of course, this is just a difference quotient. We're looking at the difference of the output values divided by the difference of the input values. And then we look at the limit as h goes to 0. And if that limit exists, we call it f prime at x. The domain of f prime, the derivative function, is the collection of all x's such that the derivative exists at x. If the derivative f prime exists, we say that f is differentiable at x. That means we're able to compute the derivative. If f prime at x exists for all x in an interval, then we say that the function is differentiable in that interval. If we just say that f is differentiable without specifying an interval or other set, then we usually mean that it's differentiable at x for every x in the domain of f. Let's compute f prime of x for a specific example. If f at x is equal to x squared, then let's find a formula for the derivative function f prime of x, and we're going to do this by looking at the definition. F prime of x is equal to the limit as h goes to 0 of f at x plus h minus f at x, and all of this is divided by h. Okay, well, the function is the square function, so this is going to be the limit as h goes to 0, and now in the numerator, wherever you have an input, you just simply square it. F at x takes an input x and then squares it. So now our input is x plus h. So we take the input x plus h and we square it. Minus f at x. Of course, f at x is x squared. And all of this is divided by h. As usual, if you simply substitute in h equals 0, you end up with 0 over 0, which is indeterminate. We have to simplify the numerator. So we'll have the limit as h goes to 0 of x squared plus 2hx plus h squared minus x squared, all divided by h. And now we notice that this x squared will cancel with this x squared, because there's a minus in front of it. So this equals the limit as h goes to 0 of 2hx plus h squared divided by h. Again, if you plug in h equals 0, you get a 0 over 0. That's because we have a factor of h in the numerator and a factor of h in the denominator. We can reduce this. This is the limit as h goes to 0. We factor out the h in the numerator, and then we have 2x plus h divided by h. The h in the numerator cancels with the h in the denominator, and we have the limit as h goes to 0 of 2x plus h. We still have an h, but it's not in the denominator, so we can simply plug in h equals 0 using the substitution rule. 2x plus 0, which of course is 2x. Consequently, we have a formula for the derivative function. If f of x is equal to x squared, then f prime of x is equal to 2x. So that means that the slope of the tangent line for a given x is twice the x value. This is a graph of y equals x squared. And we've specified a couple of points on it. For example, the point 0, 0 is on the graph. The tangent line at that point is horizontal. That's because the slope of the tangent line is 0 there. So let's just recall that our function here is f of x is equal to x squared. And we found that our derivative function, f prime of x, is equal to twice x. So this gives us a very quick formula for determining the slope of the tangent line. For example, at the origin, where x is equal to 0, we have that the slope of the tangent line, which we can call m, is equal to f prime of 0. But rather than computing it for every value individually, we just use the formula. F prime of x is twice x. Well, in this case, x is 0, so it's 2 times 0 is 0. What about this point right here? This point actually is 1.5 or 3/2. So if x is equal to 3/2, then the slope, m, the slope of the tangent line, is f prime of 3/2. But the slope is 2 times x, so it's just double the x value, so it's 3. So the slope of this line is 3. Similarly, the slope of this line is negative 3. This is x equals negative 3/2. So the slope here is twice that, which is negative 3. One thing that you'll notice is that to the left of the y-axis, all of the slopes are negative because x is negative. To the right of the y-axis, all of the slopes are positive because x is positive. You'll also notice that the slopes are negative on intervals where the function is decreasing, and the slopes of the tangent lines are positive on intervals where the function is increasing. This is the usual behavior. A derivative tells you something about how the function is changing. If the function is decreasing, the derivative will be negative, and if the function is increasing, the derivative will be positive. Let's look at another example. In this case, we'll look at the cube function. G at x is equal to x cubed, so let's find a formula for the derivative g prime at x. And again, we'll do this using the limit definition. G prime at x is equal to the limit as h goes to 0 of g at x plus h minus g at x divided by h. And this is equal to the limit as h goes to 0 of, well, g at x plus h. G is the cube function, so whatever the input is, the output is that cubed. So you take the input and cube it. So this will be x plus h quantity cubed minus x cubed divided by h. As usual, if you simply substitute in h equals 0, you end up with 0 over 0. So we have to simplify the numerator, and that means expanding that cube. So this will be the limit as h goes to 0 of, and so in the numerator, what are we going to have? We'll have x cubed plus 3 times x squared times h plus 3 times x times h squared plus h cubed. And from this, we're going to subtract x cubed. And all of this will be divided by h. The first thing to notice is that we have an x cubed at the front, and we also have an x cubed at the end. And of course, we're subtracting the one at the end. So those x cubes are going to go away. And what are we left with? We're left with the limit as h goes to 0 of 3x squared h plus 3xh squared plus h cubed. And all of this is divided by h. Notice that there's an h in every term in the numerator, so we can factor it out. That's why we have 0 over 0, because there's a factor of h in the numerator and in the denominator. So if you factor out the h from the numerator, you're left with 3x squared plus 3xh plus h squared. And of course, all of this is divided by h. So the h in the numerator will cancel with the h in the denominator, and now you're just left with the limit as h goes to 0 of something which is a polynomial, 3x squared plus 3xh plus h squared. It's actually a polynomial in h. H is the thing that's changing. X is currently a constant. It's an arbitrary, unknown constant, but we're imagining that there's a fixed x. And for this fixed x, we're computing the derivative. So we have a fixed x here, and we have some h's here, but this is a polynomial in h, and we're going to compute the limit as h goes to 0, so we can just use the substitution rule, and we'll have 3x squared plus 3x times h, but h is going to 0, plus h squared. And so the result is 3x squared. So in other words, if g at x is equal to x cubed, then the derivative, g prime of x, is equal to 3x squared. Let's take a look at the graph of g at x equals x cubed. This is the graph of y equals x cubed, or the graph of the function that we were just looking at. What we did on the previous slide is we computed the derivative of that function. We computed the derivative of g at x equals x cubed, and what we found was that g prime was equal to 3x squared. This is the slope of the tangent line at a specified x. So this is the slope of the tangent line for a given x value. For each x value, there is exactly one corresponding y value. So once you know the x value, you can compute the y value using the function. That's what it means to be a function. You give it one input and it will give you one output. So once you know the x value, that specifies a point on the curve. And the derivative of that function tells you what the slope of the tangent line is at that point. And here we have a nice formula for it for this function. So for y equals x cubed, if you specify a point by its x-coordinate, then the slope of the tangent line at that point will be 3x squared. So one thing that you might notice is that the derivative 3x squared is never negative. It's 0 when x is equal to 0. That's at the origin. That's why you have a horizontal tangent line there, because the slope of the tangent line is 0. But everywhere else, it's positive. And you can see that for any x value other than x equals 0, the tangent lines will have a positive slope. This corresponds to the fact that this function is increasing. The function g at x equals x cubed is an increasing function over the entire real line. And because of that, the derivative is always non-negative. It's 0 at this one spot at the origin, but other than that, it's strictly positive. Something that helps understand what it means to be differentiable is to take a look at what it means to not be differentiable. For example, a function is not differentiable when the graph has a corner. This is the graph of the absolute value function, and it has a corner at the origin. If there's a corner, you won't have differentiability. In this particular example, you can see that f at x is equal to x when x is greater than or equal to 0, and it's negative x when x is less than 0. The derivative is going to give us the slope of the tangent line, but in this case, both pieces, the piece where x is positive and the piece where x is negative, is the graph of a line, and so the derivative is just going to give you the slope of that line. When x is positive, the graph is the graph of the line y equals x, and the slope there is 1, and that's why when x is greater than 0, the derivative is 1. Similarly, when x is negative to the left of the y-axis, the graph is y equals negative x. That has a slope of negative 1, and that's why the derivative, when x is less than 0, is negative 1. What about at 0? The difficulty is that when you compute the derivative, it's a limit from both sides. So as you approach from the right, you're going to get 1. As you approach from the left, you're going to get negative 1. And what does that mean? That means that the derivative doesn't exist at that point because the limit defining it doesn't exist at that point. Another occasion when you won't have differentiability is when the graph has a vertical tangent line. So this is the graph of the function f at x equals the cube root of x, and it's not differentiable when x is equal to 0. That's because the tangent line there is vertical, it's the y-axis. Later on, we'll show that the derivative of the cube root of x is 1 over 3 times x to the 2/3, and this has an infinite discontinuity at x equals 0. That is to say that the limit as x approaches 0 of the derivative is infinite. And what does that mean? That just means that the tangent lines are getting steeper and steeper as you get closer to x equals 0. You can see that the tangent lines always have positive slope, but they get quite steep as you get close to x equals 0. And in fact, when you're at x equals 0, you have a completely vertical tangent line. And then they're still positive after that point, but they're not quite as steep. But the fact that there's a vertical tangent line means that the slope is, you could say, infinite, but infinity is not a number. It's the idea that something is growing without bound. And in this case, the thing that is growing without bound is the derivative. The slopes of the tangent lines are growing without bound as you get closer and closer to x equals 0. A function is also not differentiable at any point of discontinuity. For example, here we have a piecewise defined function. When x is less than or equal to 1, the function is given by the parabola x squared plus 1. That's this part right here, to the left of 1. We have a nice parabola opening upwards. That's continuous, that's differentiable, everywhere except at this jump at x equals 1. Because at x equals 1, it becomes a new function. And that new function is minus x squared plus 5, which is now a downward opening parabola. This function, too, to the right of 1, is continuous, and it's also differentiable. The only problem is that we have a point of discontinuity at x equals 1, and the function is not differentiable at that point of discontinuity. We can show that directly by trying to compute it. If f is differentiable at x equals 1, then we can compute the derivative f prime at 1 using the limit definition. The limit as h approaches 0 of the difference quotient, f at 1 plus h minus f at 1 divided by h. So the question is, does this limit exist? Let's try to compute the right limit, and we'll see that there's a problem. The right limit is when we're coming in from the right, so from numbers bigger. So what does that mean? Well, let's take a look at it. So we want to compute the limit as h approaches 0 from the right. So h is a positive number. It's a positive number which is slightly bigger than 0. And here's our difference quotient, f at 1 plus h minus f at 1 divided by h. Well, the first thing to do is to compute f at 1 plus h. So we come down to our definition for f at x, and it's piecewise defined. What is our input? Our input is 1 plus h, but h is positive. H is a positive number because h is approaching 0 from the right. So what does that mean? That means we're adding something positive to 1. So 1 plus h is slightly bigger than 1. So in our rule here, we're using the bottom rule. We're using the rule where x is bigger than 1, because 1 plus h, since h is positive, 1 plus h is slightly bigger than 1. So we're using this bottom rule. So that means we take the input and we square it, put a minus sign in front, and then add 5. So let's do that. So we'll have minus the input, 1 plus h, quantity squared, and to that we're going to add 5. So that's the f at 1 plus h. That's that part. What's next? Well, we now have to subtract f at 1. So we're going to do minus f at 1. But what is f at 1? Well, when x is actually equal to 1, so if x is less than or equal to, which includes the equal, we're using the top rule. So we have x squared plus 1. So this is going to be 1 squared plus 1. And this is the top part. So let's change the color, and that's this part right here. Okay, so let's just compute these things now. Of course, this is the numerator of the difference quotient. We're dividing by h, of course, because that's in the denominator. So let's simplify the numerator. We're going to have minus, and let's square 1 plus h. So that's going to be 1 squared plus 2 times h plus h squared. And to this, we're going to add 5, and then we're going to subtract 1 squared plus 1, which is 2. Okay, so we're going to have minus 1, and then it's going to be a minus 2h minus h squared plus 5 minus 2. All right, so the limit as h goes to 0 from the right, let's get all this together. So we have a 5, and then we're subtracting 2, which is 3, and then we subtract another 1, which is going to give us a 2. So we're going to have 2 minus 2h minus h squared in the numerator. And we're going to divide that by h. Just for fun, let's just highlight all of these constants. These are the things that we're combining into that 2. Everything else is unchanged. Now notice what this equals. Notice that there is no factor of h in the numerator. There is an h in the denominator, and there are some h's in the numerator, but this 2 doesn't have an h. So we can try to divide everything by h. So we'll have the limit as h goes to 0 of what? Well, it's going to be 2 over h minus 2 minus h. And what happens to this as h goes to 0? Well, this part goes to 0. This negative 2 goes to negative 2, it's constant. But what about this 2 over h? As h is going to 0 from the positive side, well, this term, that's going to become infinitely large. So this limit doesn't exist. Does not exist. So the limit doesn't exist. That means that the derivative doesn't exist. Remember, the limit we're trying to compute is the limit of this difference quotient. We're just looking at the right-hand limit. So this limit doesn't exist. So that means the derivative doesn't exist. So the function is not differentiable at 1. And this sort of thing will happen when you have a point of discontinuity. So this is a theorem. If a function is differentiable at a point, then it must be continuous at that point. Now you have to be careful about what this means. If it's differentiable, then it must be continuous. But you can have a function which is continuous and not differentiable. And we saw 2 examples of that. One example is the absolute value function. That function is continuous at 0 but not differentiable. And we also saw the cube root function. That function is continuous at 0 but not differentiable there.